Good afternoon. This is Mr. Goodfellow. I prefer to go by Mr. G, but you guys have probably seen me in the building before. But at Reno High School, I teach pre-calculus and trig, as well as Mr. Leesman and Miss Merzak. But they've asked me to make all the videos for this moving forward stuff that we're doing now for our digital learning. And the nice part about us doing this digital learning stuff for pre-calculus is that we're going to start covering some materials that will be helpful to you as you move on to either AP stats or AP calculus. So the two sections that we're going to be looking towards are going to be one that's about chapter 11 in your textbook, about sequence and series, and another one that's going to be about calculus, an intro to calculus over the next few weeks. So I'm going to lead you through all of the actual material that this is in touch with. And we're going to start with a little intro to sequence and series. This is 10.1 is what it is. These materials can be found in your Teams app, and you can find these in your files. If you want to print these out, you're more than happy to print them out. But if it turns out that you just want to take notes on regular pieces of paper, or whether or not you just want to rewind the videos, that's totally possible too as well. We won't be doing any of the review questions that are listed here in the beginning because they kind of go back to some stuff based on trig and into parametrics, another section that we didn't get a chance to take a look at. So we will continue, and my board here is being really super sensitive. Okay, we're going to try my best. My control key keeps turning on. I don't like it. Okay, so the idea of sequence and series, and the idea about sequence and series is going to be about what do these two words, first and foremost, what do they mean? Okay, the word sequence is the first one that we're going to really talk about. And it says here a really simple definition is the sequence is just the values of a defined pattern. And a lot of the stuff we're going to be talking about in this particular chapter is going to be about pattern recognition. Now, let me give you just an example of a sequence. Maybe we were going to talk about just the even numbers, okay? So if I say the even numbers, we know them like 2, 4, 6, 8, 10, and so forth down the actual line. These are even numbers. Now, that represents a pattern that's going to be going on. This particular concept right here would be referred to as a sequence. So a sequence of numbers. Now, we do a lot of discovery on this because sequences do show up in lots of different places in mathematics, and about how we are going to manipulate them and use them is going to be important for the future. Now, when we start talking about a sequence, it's important for us to understand there are different kinds of sequences. There are different notations to the sequence and so forth. Well, the first notation I really want to talk about is that when we look at the very first term of a sequence, we can call it the first term of a sequence. Then later on down the line, like say we would call this the first term, the second term, the third term, the fourth term. This would be the fifth term of the sequence and so forth. Now, the notation that we use in that particular regard is that instead of just saying, the first term is 2, we say a sub 1. And what this is basically saying is that the element that you're talking about, I don't always they use E, but they use an A. The element that you're talking about is the first element of the sequence. So we would say a sub 1 is 2. Whereas this one down here on this end, we would say a sub 5 is equal to 10. So you can actually start to list each term in the sequence as not only what its value is, but where it exists in the sequence itself. So this is the first term, that's the second term, this is the third term. This would be a sub 4, and that would be the number 8. Okay, so get the idea of what the notation means, because it'll be very, very helpful. Now, if they use a notation that says a sub n, this a sub n is meaning that it's in place of everything that wherever you want it to be. So if I wanted to be at the 5th, I'd put 5 in there. If I wanted to be at the 10th, I'd put 10 in there. So this is basically saying, where am I right now? Okay, I like to think of this word right here as a sub n as being the present term. Where am I at this particular time? All right, that'll be important because when I start talking about recursive, I'll talk about the present and the past and the future, and those kind of things will matter. All right. Now, the second thing we're going to talk about is, other than the idea of there being sequences, which are just lists of numbers, what are some of the things that you can do when you discover those sequences? And one of them can be finding its series. Now, a series is the sum of the values that are in that particular pattern. So let's say I'm still dealing with those evens up there. I wanted to find the sum, and they use a big S for this, of the first 5 terms. And that would be that I would be adding up a 2 and a 4 and a 6 and an 8 and a 10. And I would get the sum of those first 5 terms. So that would be something like 10, 20, I think that's 30, 10, 20, and 30. Oh, so the answer with that would be 30. All right. Now, they use this notation of the S for sum, but sometimes you will run into some books that use a sigma notation just as easily. Now, this happens to be what's referred to as sigma. Okay, that's the symbol for it in Greek lettering. I'm going to roll down just a little bit right here. And what it stands for is it stands for sum as well, too. Now, you're going to see a couple of these where we're going to expand these sums, these series out, and actually find their sum. Now, to do that, what we have to do is we have to understand how the sigma notation actually works. Now, the sigma notation is saying sum, but you want to say summing from where to where. So the first number that's down here on the bottom will be where you want to start the sum from. And the number that shows up in the top will be where you want to end in terms of the sum. Now, this is in terms of x. So you might see on the bottom of this, it'll say x equals 1. And then I'm going to say, let's sum this all up to the third term. Now, what is that summation actually going to do? Well, it's going to start on the first term, and then it's going to sum the next integer in there is going to be the second term, and then it's going to go to the third term, and then it's going to end. So it'll do this concept. It'll go 2 times 1 plus 1. That would be the first term. And then it's going to use that same formula again to find the next term, which is going to be 2 times 2 plus 1. And then it's going to find the third term, which is going to be 2 times 3 plus 1. And that's what that summation notation is really saying. I'm going to add the first term, the second term, and the third term based on this equation. Okay, so there's a beginning and an end, and this is usually referred to as the explicit formula, is what this is called. And we'll talk about more about explicit formulas and what they are. Now, that answer to this whole entire thing would be something like 2 times, that's 3, plus 5, plus 6 and 1 is 7. And the total answer for that summation would be 12, would be 15. All right? So that's what that summation is saying. It's either write it in the S notation or you'd write it in the summation notation. Now, some things that happen when you have summations like this is that you can do specific things to them. First, for instance, scalar multiplication. What if I put on the outside of this a 5? And I was still going from 1 to 3. Well, this particular piece we just figured out. The whole answer to that was the number 15. But if I just have a scalar multiplier on that, it's just saying multiply the sum by 5, and you would get the total answer of 75. So scalar multipliers on the outside of a summation just work as multiplication. Okay. Now, these explicit formulas for summations can come in all kinds of different forms. This one, there was a missing division here. Let's say I wanted to sum it from, maybe I don't want to start at 1, but I want to start at 0. Now, this would be, if we're thinking about terms, a sub 1 would be the term that's right here in the first position, but a sub 0 would be the actual term that came just before it. That's okay. Usually we like to start our summations with 1, but I would say that starting with 0 is not a bad thing. It's just unaccustomed. We just don't do it very often. Okay, now the next one we're going to do here is, let's say we wanted to go from 0 to 2. Well, that would be 4 minus 5 times 0 divided by 2. added to 4 minus 5 times 1 divided by 2. It always goes up by one integer each time. And then plus 4 minus 5 times 2 divided by 2. And you would figure out each one of these. That's 0, that's 4, that's 2. Or 2 over 2. Excuse me, 4 over 2. 4 over 2 plus, that would be a negative 1/2. And then this one would be negative 6/2. Okay, so we've got negative 10, 4, and then that makes sense. And if I add all my numerators together, I'd end up getting negative 3/2 would be my answer for that series. Okay, now those series concepts or sigmas come in all kinds of different shapes and forms. Okay, they can have all kinds of explicit formulas. This one right here might be a new one for you that you've never seen. This is referred to as a factorial. Okay, and it has an exclamation point as its notation for it. And what it is that math teachers don't like to write out multiplications, specifically successive sequence ones. Like, say I wanted to write out all the numbers from 5 down multiplied by each other. So 5 times 4 times 3 times 2 times 1. Yeah, that's a lot to write. So instead, we write it as 5 factorial. And that's what that notation means. It's all the successive integer multiplications from 5 down to 1. Okay, now if I was going to simplify something like 8 factorial divided by 7 factorial, well, 8 factorial would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's a lot. And then this one, 7 factorial, would be 7 times 6 times 5 times 4 times 3 times 2 times 1. And this division actually works out kind of nice because, whoa, look, they all cancel each other. And the answer in the end would be 8. Wow, that's cool. Kind of a jump ahead. Do you think we could probably come up with 33 factorial divided by 32? I don't want to write it, but that 32 factorial would take care of all the 32 to 1 on the top. And the answer would be 33. Okay. Now, when it gets a little bit more complicated, it's when it actually turns out to be letters. Now, n plus 1 factorial would be n plus 1, and then it would be multiplied by 1 less than that, which would be just n. And then it would be 1 less than that, which is n minus 1. And then 1 less than that, which is n minus 2. And I just keep going down the line. It doesn't really tell me where to end. Now, if I divided that by n factorial, which would start at n, and then it goes down by 1, that would be n minus 1, and this one would be n minus 2. It looks to me like there's some cancellations going on here too as well. The n's, the n minus 1s, the n minus 2s, and the dot, dot, dot go away, and the answer would be n plus 1. That was what it comes out to be. Okay, those kinds of ideas of dealing with it in terms of variables ends up making it a little bit more difficult, but not too hard to understand. Okay, sigmas can work on powers. Like, say if I was saying x is equal to 0 going to 2, that would be 3 to the 0 plus 3 to the 1 plus 3 to the second. And ultimately, that'd be 1 plus 3 plus 9, or an answer of 13. Okay, seems pretty makes sense. Now, things where it doesn't make a whole lot of sense is things like cosine. It does, like x is equal to 1 to 5. We don't really plug integer values into cosine. We like to plug things like pi over 4 and pi over 3 and pi over 6. And so when it comes to trig, these are like, it doesn't really work as well as we would like it to. Specifically because those ideas of trig don't work on integer basic concepts. All right. Now, this is video 1 of 10.1. Now, I'll use the continuation of the second part to do some of these problems that are in the 10.1 series down below.